get started on my actual teaching is, so this is going to be the first lesson on my unit, which is on phases of liquids, or gases, liquids, and solids. So this is going to be talking about gas laws, so we're going to be talking about the gas phase. So right now, I have on the agenda, so I want you guys to start out by drawing in your balloons, if you read, so if you read the directions at the top, does somebody want to read those for me?
Gotcha.
Thank you.
Assume that all balloons have the same amount of air inside, but balloon number 1 is kept at 5 degrees Celsius.
Correct.
And balloon 2 is kept at 25 degrees Celsius. And balloon 3 is kept at 50 degrees Celsius. Draw what the molecules inside each balloon would look like.
So if you guys could all do that now for me. Draw what you think the molecules inside look like.
Okay.
Do you want us to draw them in a special way? Like do?
No, I want it's whatever you think. It's 100% whatever you think it is. This is the very first day on the lesson, so you have no prior knowledge of what we're talking about, or maybe you do. That's what. So we'll do that for a second. I hope they are. You have a science background? Maybe. Oh, okay. Okay. So I think most of you are done. So for balloon 1, what does it say? It's at 5 degrees Celsius. So Garrett, why don't you tell me what does yours look like?
So I just put dots in the balloon for my molecules, and I just kind of put them all kind of close together.
Okay. Why did you do that?
Because colder temperature, they're going to be more condensed.
Okay. So something like this, closer together. Imagine this. What am I trying to say? The same thing. Everyone's doing right. Tightly packed. What are you getting at? Okay.
Just closer.
Sean, what did you draw for your balloon at 25 degrees? Balloon number 2.
They're real spread out. They're moving around.
Okay. Real spread out, so like more than you had in.
Oh yeah, definitely.
Yeah.
Yeah.
Why'd you do that?
Because when things heat up, they tend to, I don't know, like get active. I guess molecules get bigger and they.
Okay, so they're a little bit more sporadic.
Yes.
Something like that. Okay. And then how about up here? What did you have for balloon number 3?
I did like little circles for my thing, and I put like little lines behind it, like show speed, because I figured at 50 degrees Celsius to be moving faster than the other 2.
Interesting. Okay. So it looks like you have a direction for yours. So yours are just kind of flying around.
Just like a random direction. Yeah.
Random direction. Okay. I like that. So just his looks like this.
Yeah.
So he's got molecules and they're just bouncing off the walls everywhere in there. And I think that's a really good description. And I think you gave a really good description. So when air heats up, the molecules, they get excited and then they start to move around. So they're going to start bouncing off the walls, be flying all over the place. They're not going to be as tightly packed like a lot of you described for balloon number 1. And that's what we're going to talk about today. Why that happened and how that affects things. So today the focus is going to be on Gay-Lussac's law, which was developed by Joseph Louis Gay-Lussac in 1809, which you don't have to remember that. Does somebody want to read to me what the law states? Sean?
The law states such that volume is constant for a given mass of an ideal gas. The pressure of the gas pushing out on the walls of its container is directly proportional to its absolute temperature.
Good, okay, so that's a lot of pretty big words. Does somebody want to try and break that down for me, kind of in the layman's terms, what that might mean? Creighton?
There's gonna be less stuff in a smaller thing compared to more stuff in a bigger thing.
Why do you think that?
Because like, if you have something small, you can't fit as much stuff into it. If you have something bigger, you can put more stuff into it.
Okay, does anybody else want to try? Yeah?
And maybe it means that the warmer it gets, the more is going on there, so, the more warm I have, the more the molecules move.
Right,
and
okay.
push them out.
Yeah, I like that. So if we bring that back to the balloon models that we just drew. So balloon number 1 is really small, and you guys drew the molecules really tightly and compact on balloon number 1. That's because balloon number 1 is at a lower temperature, so the molecules are going to be less active, and they're going to be moving around less, so there's less pressure on the walls in the balloon, thus the balloon is going to be smaller. But then in balloon number 3, where we had it heated, the air inside it was heated up, the molecules are then excited, and they're bouncing around, they're moving around all over inside the balloon, and all that movement from the molecules is putting more pressure on the walls internally in the balloon, causing it to expand. So, good explanation. So, like we have here, balloon number 1, the balloon with the smiley face on it, what kind of assumptions can we make about that balloon? Just by looking at it. Yeah?
That it's bigger than the right one, and so there is, the temperature is maybe higher than the
Okay.
other one.
Yeah. Okay. Anybody else want to take a stab at it? Sean?
It's full of something.
Yeah, okay. Full of something. I mean, it looks like there's something pushing on the walls of it. Looks like it's not really a whole lot of room to spare on the inside of it. Sure. Anyone else? What about temperature? Temperature,
I
yeah.
bet it's pretty warm because it's big, so it's
Okay.
gonna be at a pretty high temperature.
Okay. So then what about the other balloon? What temperature would that
It's at a
be?
lower temperature,
Correct.
so it's colder.
Yeah, okay, very good, very good. So, from Gay-Lussac's law, we then can derive the pressure law. So, pressure law states that if we know that pressure is proportional to temperature on the inside of the container, we can sometimes, we'll talk about that in another lesson, why that's there, but we can sometimes make the assumption that the same is true for the outside of the container. Thus, we get the relation that the pressure inside of an object and its temperature are proportionally related to the pressure and temperature outside of the object or another container that would be connected to it. And once again, we can then derive that law into the combined gas law, which is expressed as such, but we're not going to talk about that too much yet. So what I want you guys to do now is, in groups of 2, flip over your sheets. Oh, actually, I'm sorry, I denied myself. Flip over your sheets though, please flip over your sheets. And at the top of it, you guys will see the equations that we just talked about. And does somebody want to read this question for me? Yeah, go ahead. Oh, go ahead.
Alright.
Oh, no, sorry, the question on the board.
Oh,
I'm sorry.
okay.
Yeah.
A gas has a pressure of 499 psi at 123 Kelvin. What is the pressure of the gas with when it is heated to 321 Kelvin?
Yes, okay. So, looking at